All right, it's class time. So, today we're going to be doing some more interesting stuff. Remember back in the day when I promised you that we'd be learning how to generate stuff? Today's the day, and next homework is the homework. Hope you're all excited for that. So, first I want to talk about homework 3 a little bit, just real quick. No long debate on this one. So, 1. I am having you submit a PDF, not a Python notebook. The reason for this, in case you're curious, is because if we submit a Python notebook, then the graders are going to have to scroll through your entire code, and that's awful. As a PDF, you can mark certain pages, so I'm doing it like that for the graders. There are online converters, and if you are using Google Colab, you can just download it as a PDF, so I believe in you. You are CS students, so good luck. You can also ask, and I can give resources if you need. Next, a couple of people have posted different comments on Piazza, I think privately, pointing out different mistakes in the code. There's no mistakes. I'm perfect. Although I really have not seen any genuine mistakes on the code given, so far don't worry about that. I know that was an issue on the last homework, but on this one, hopefully I did a little bit better. And then a very valid concern is right now running the Python notebook, you're running it on your own computer if you're using Jupyter. And as we deal with bigger and bigger models, your computer might not be able to run these models, might not be able to train these models. So all of these models and all the homeworks, I'm going to test on Google Colab to make sure that they can be run. If you're having trouble with the model that you choose, I am letting you design your own models a little bit. Lower the number of parameters, and you should be fine. They should not be too computationally heavy. We're just doing a couple layers. We're not doing big networks. Yeah? Are we doing anything with Google Colab's GPU? You can. I have not been doing that. It's just an extra thing. In case you're curious, if you run it on, so it's called CUDA, is NVIDIA's particular way of dealing with tensors. And it is a little bit faster for large models. It's actually not much faster for big models or for small models. So for us, it's not a big deal, and also it's just a hassle. So let's not. If you are curious, though, look up CUDA. And next, I wanted to just get a quick, dirty poll. Was this homework better than the last homework in terms of stress and all that? Thumbs up or thumbs down? Or cool? I think unanimously. Oh, yeah, unanimously. OK, cool. All right. That's good to hear. That's improvement on my behalf. Cool. The rest of the homeworks will be in a notebook form. One last little side note. So for homework 6, which is a while out, I am planning on having us make RL agents to play competitive games with each other. If you have a suggestion, I'd like to make a tournament out of it where everyone makes a bot in the tournament. If you have a suggestion of what game, send me a message. Cool. So that's that. All right. Now, midterm stuff. So, midterm is 1 week from today in class. Scary, I know. The intention with the midterm is, again, not to be difficult, but there is a chance it turns out to be difficult, in which case everything will be scaled. No big deal. So don't stress about it too much. Just try to understand the material. On Wednesday, we'll be doing a review session. As much of it as I can. It's essentially the entire material of the class is going to be in it up until the end of this lecture. So this lecture is material that will be on the exam. Yep. And this is me saying that it's not supposed to be like that. It is going to be a lot like the quizzes in terms of format. There'll be true or false, multiple choice, and then open questions. And those will be a lot like the quiz questions, except easier. Cool. Also, completely open note, this is not going to be the type of exam where having memorization is going to help you. Not that you shouldn't remember stuff, but as long as you have it on paper, you can bring any notes you want. Okay? You can even print out the slides if you really want to. Don't get bogged down bringing too many notes. I've seen a lot of people slow down by looking through all their notes, so do try to remember a good amount of it. Cool. All right. So, we start with a big question. What do we do if our data doesn't have any labels? Any guesses? Yeah?
Unsupervised learning.
That's a pretty good answer. I'm going to say for now we give up. We need data, right? We can't do anything without data. But that's not exactly true. And in fact, we still have data, right? And there are things that we can do as long as we have data. And the answer, as you might know from the syllabus, or as Ruchira just said, is unsupervised learning. So the paradigm now is before we had inputs and outputs, or these labels for our data. And what we're going to do now is we're going to take away those labels. We don't need them. We still have our inputs, though, and there are things that we can do with that. So we're going to explore that idea of what we can do with that. All right. So give a second to think of what you might be able to do with just inputs. All right, actually take a minute and think about it. Any ideas? Yeah?
Generate outputs like random.
We could generate outputs. We could try to give outputs that are similar to these inputs, which we'll be doing later. Yeah? We can cluster similar things. So we could take things that are like each other in an arbitrary way and cluster them together. Neat? Yeah?
We can do statistics on the inputs, like most frequent input or most often.
Yeah, we can do statistical analysis. Who needs ML, really? I mean, it's arguable whether some statistical analyses are ML, but for now, let's say they aren't. Yeah, these are all perfectly valid things that we can do with this data. Let's look at these two ideas in particular we are going to cover. Let's start by just plotting some data. All right, let's say we have this data. What do we notice about this data? It's two clusters. See how you all identified that? Look at us. So it's pretty clear to see that there are two different groups here, right? So it seems that if we can see it ourselves, it'd be probably likely that our machine learning model can do this too. And these, as pointed out by Adam, is clusters. So we think of these as clusters. In this case, they are physically close to each other. We'll talk about other ideas of that next. And one thing you might ask is, OK, this is a very clearly set up example, right? I just put a bunch of clusters of data next to each other. Can this happen in the real world? And in fact, it very much does. That's the main attribute of real data. I mean, anytime we're doing any sort of these analyses with machine learning, we are noticing these things that exist in real data. It'd be very difficult to find data that doesn't do this, actually. And here's an example of what this data might look like. If we had this was hours of studying, this is just relating it to the other one, and we had hours of video games, then we could see that we could have some sort of pre-labeled, or we could have these clusters that automatically we can label. These could be good students, and these could be gamers. And we can see that they are discrete groups. So clearly this sort of stuff can exist in real data, clearly. Let's look at something a bit more difficult, though. Let's say we have this data. And the first thing that you should notice about this is that I have colored it already. But if we're just looking at this data without any labels, there is nothing. So I've given you the labels here. And what I'm saying is that these blue dots have some different properties than these yellow dots in some way. Right? And I'm giving you that as a label, but I'm just telling you now so we can think about how we might extract those differences in data that is very muddled like this. Right? So we know that in a case like this, imagine that these are very different behaving inputs, right? Maybe they're gamers and good students. And so our model, it would be very helpful for our model to know whether one of the inputs is a gamer or a good student for it to determine whether or not they'll fail the class. So in the case of this, being able to cluster this would be very helpful, right? But how might we be able to do this? So anyone have any ideas of how we might be able to separate these groups? This is going to be the punchline for the first half of the lecture, so it's OK if you can't think of the answer now. Yeah?
Can we have more dimension, like more features to describe the data?
So that is something that we can do. So if we added more features to this data, we might see that maybe in this dimension they're very muddled, but in a different dimension they're very separate. And then it's very easy to separate them. In this case, I'm saying this is all of our data. This is all we got. In this case, it's very hard to tell. So, in particular, I want you to think, is there some task that by performing the task, we would end up with separate clusters, and that task only depends on the input. We don't need any labels, just the input.
You want this kind of shit though, out of the task?
Sure. So we want to find some sort of clustering. In this case, I'm telling you that this is a good clustering. I'm just telling you right now this is a good clustering. How might we get that good clustering? Yeah?
Is it like MSC on a parabola or something? Square letter on a parabola.
So perhaps you could try something like that.
Something close to it.
Yeah. This is going to get to. I'm going to give you a slightly better punchline, I think. So this is a hard problem, right? In particular, this two-dimensional example is very difficult for you to think about, right? And it probably is not a tremendously good example, just a much more visualizable one. But let's look at a general solution to this, which is a very clever and very simple idea, right? Called an autoencoder. All right. So let's imagine we have some data, and what we would like to do is we would like to have a neural network that learns how to cluster the data automatically in some useful way. So that would be if we have this data, we could have a transformation done by a neural network that would transform the data into something like this. Very usable. So it seems like this would be totally possible if we had these labels, right? If we label these 1 and these 0, and we have our model trained, we can learn that little swoosh. That's fine. But again, we don't have any labels. So how can we automatically extract good clusterings like that? And what we realize is that when we're doing other tasks, say the MNIST digit classification that we're doing in homework 3, when we're doing that, we are kind of automatically doing this. Think about each time we do a layer of a neural network, we are transforming the space, right? And I'll tell you now, we are doing something kind of like this. Right? We are trying to separate like things. We are trying to find important features. That is actually a big point of the entire convolution homework, is that we're extracting important features. So it's doable with these tasks. So we need some task that is just reliant on the input. So say we have some image like this. How could we define some task where learning that task would give us good features like that? Give it a minute to think. If you haven't already heard about these, then if you can come up with the answer here, then you have discovered something very interesting and useful. Give it a second to think. All right, anyone have any ideas? Besides people who have already heard about it? Yeah? Oh, yeah. Okay.
In this case, like a really basic idea would be just separating background from foreground.
So separating background from foreground. So that would require a little bit of pre-processing. So we imagine in the case like that, we could use some other tool to say, okay, this is the foreground, this is the background, and then we want to be able to identify which is which. That's a segmentation map. That is definitely possible. That is definitely possible. There is an easier thing that we can do, and let's imagine we don't want to do any pre-processing. Crazy. We don't want to do any. Yeah? Oh, yeah? Cluster similar colored pixels. That's a good idea. That's a good idea. So that is something that we would get doing something like KNN, which is a traditional way of doing clustering. This is something that we're not covering in this class because we are doing more, an overview of slightly more modern things. It is a bit of an old school thing, but it is an idea that works. Here is going to be a beautiful little thing that we can do. We can make our task to take this input and use it as the same label. So we're taking the input and we're producing the input. All right? So let this sit for a second and see if you have any problems with that. What we're trying to do is we're taking our input and producing the same image, and what we say is that if the network is able to do that, then it must be extracting everything that is important about the image to be able to reconstruct it. There is a pretty big issue with this, though. Anyone notice it yet? I'm going to let you talk in your groups for a couple of minutes, see if you can think of any issue with this. All right. You had time to think? Anyone have a big issue with this yet? Yeah.
Thinking that if you have an input and you run it through the loss function, once the loss will equal 0, basically it's just saying that the input equals the input, so all the weights would basically just make it so that you have an image and produces itself.
So you're getting very close to the exact right words I wanted you to say. Not quite, but it is the right idea, which is, let's think about this. Imagine we have a network that is just a single matrix multiplication from the input size to the input size, right? What matrix would give us exactly this behavior? I know some of you haven't taken linear algebra, but yeah? The identity matrix. The identity matrix, in case you don't know it, is just ones along the diagonal and zeros everywhere else. And it produces exactly the same as the input. So if we had a network like this, it would exactly produce that. All right, we'll pin on that for a second because someone pointed out something good, which is I didn't actually ever define what an unsupervised learning is, which I did kind of breeze over, but I think it's very good to take a second and fully identify it. Supervised learning is we have inputs and outputs, and we're trying to learn how to translate these inputs into these outputs. Unsupervised learning is any task where we don't have those outputs. We are just given the inputs. In that case, we can say that the supervision is us saying that was the right answer or that was the wrong answer. In the case of unsupervised, nothing is telling us that. We don't know if these clusterings that we're doing are good. We are just doing clusterings. Yep. So they do have a bit of a weird thing. There is also self-supervised, which you could make the argument this is, where we tell ourselves what we're trying to optimize. In this case, being reconstruction. Yeah. Yeah.
This is just like a request. Do you think it's at all possible for you to have a slide eventually?
Of what unsupervised is?
What, just like supervised versus unsupervised?
On Wednesday. How about that? Yeah. Thank you for reminding me. All right, cool. So if we were to train this naively, we would just end up with the identity matrix if our model trained well. That's an issue. That is nothing. That doesn't extract any features. That's not useful in any way. So just learn the identity function. So how can we avoid this happening? Again, think on this for a second. Just continue to think for a second about it. I'd like for people to have a chance to think on themselves. All right. Yeah. Masking? So are you saying masking part of the inputs and giving you back the same output? Interesting idea. It still is not solving the fundamental problem, but it is a nice idea, and we're going to talk more about that sort of thing later. Again, you're doing data augmentation, so you're creating a situation where your input and your output are different, which is not exactly autoencoding. This paradigm is really we take the input and we reproduce the input, and in that process learn stuff. Any other thoughts? I think you had your hand up.
Well, I was going to say maybe, because like our model being an identity matrix is kind of like a trivial solution.
Mm-hmm.
So if we just like not allow a trivial solution.
Explicitly disallow the identity matrix. That'd be interesting. We would still probably end up with something approximating the identity matrix, depending on how thoroughly we say do not be like the identity matrix. That might work. That's an interesting idea that you could like try out on your own. I don't know how it would work. Yeah.
When we convert our inputs to labels, could we like modify it so it's not exactly the same? Like modify the input in some way?
So that you two are really vibing right now, which is if we do change the input and output, we do get different behaviors. There is a pretty fundamental issue going on here that I think no one has quite touched on yet. I think I'll let Autumn tell the punchline here. Yeah?
I don't know if it is. But
Oh, cool.
You can reduce the features, so you don't keep the features the same size.
That is exactly what I was going to try to have you say, which is we want to make the network compress the data. So good ideas all around, but this is a very simple and elegant thing that is what an autoencoder does. We're going to compress the data. I'll show you what I mean by that. So we're going to take our input, and we're going to reduce the size of it, and then we're going to expand the size out. So a way that I like to draw this, and you may see around, is something like this, where we have an encoder and a decoder. And then in the center, what we say is that we have encodings of the features of the input, or the encoding of the input, if you'd prefer. So in doing this, we guarantee that at the very least, it is having to consolidate some information, do some sort of clustering, like we were talking about before, of the input to be able to reconstruct it. We also guarantee that if it's able to do a very good reconstruction, that those features, those embeddings, I'm saying a lot of things that are equivalent in this case, but those encodings or those embeddings, which are the same thing here, must be descriptive of the input, must be very good if we're able to reconstruct it. So we've extracted now, we can guarantee useful features. And this paradigm is a very useful one, and it's very simple, which is very nice. And from this, you'll see this if you look at more modern models, lots of them use this kind of concept. So you can sit on that one. It's very nice and easy. Yeah?
So will we have a network that would basically have like a certain amount of layers, then less layers in the next, or less like
Size. Yeah. Dimensions is the word. Yeah. Yes. No. Exactly. So we would reduce it, and at some point blow it back out. And there are different ways that you can design these autoencoders. I've shown here a very simple one, which is just essentially 2 layers where we just go to small and then we go from small to big, and we just call it a day. That would work. That is a perfectly reasonable autoencoder. It's not very good because it's not using any of the other tricks that we have, like convolution, but it is reasonable. So yeah, that is the idea of autoencoders. Wonderful, right? There are a couple more things to talk about autoencoders, though, even though that really is the whole punchline for them. There are a couple more things that we can take away from them. Firstly, Let's say that we take just the encoder part. So that would be just this bit where we go to the middle features, right? Those embeddings, those encodings of the image. And what if we say, all right, those are no longer going to learn, right? Let's just put them in a box. Let's say those aren't going to learn anymore. They are creating good encodings. And then we take the output of that, and we feed it through another network. In this case, it's just a layer, but another network that treats now the output of this encoder as its input, and then does some other task with it. In the case of this, maybe identifying the age of the person, or whatever. And by doing this, we're able to leverage these embeddings that we've had before. So we had some unsupervised training that said, OK, now on these images of faces or whatever we're training on, we can get these good embeddings. And now we can use them as the input to another task. And this is the purest reason why we want to use autoencoders. Yeah?
And so the goal of this would to be to make like things more computationally less expensive, like for other.
So not even just that. So if we were to, so it is true that now we're just training on autoencoding and then we're training on this, and we're training less network, which is good for us. So that is definitely an upside. But more than that, we've now trained on this really big set of unlabeled data, right? Imagine we have 100,000 images of people that do not have any label of like their age or anything like this. We train this encoder on all of that data, right? And now it's able to look at an image and find really good features to extract. And now imagine we have a data set that tells the age of a person, and we only have like 2,000 pieces of data. Now using those 2,000 pieces of data, we can train the rest of the network while leveraging everything we already learned. So this is one of the powers of unsupervised learning, is there is much more unlabeled data. So there's that. There is the fact that it is reducing the feature space at these later layers, which is also very nice. And it is also that doing it through autoencoding is explicitly getting us good features that are good for a variety of tasks. So this would be usable in a whole bunch of different scenarios. And this is, again, the core idea of this autoencoder and why we would use it. It is an interesting idea that we are able to compress data. You know, you can think, oh, maybe I'll make a compression thing or whatever. But this is the main reason why we would want to do this. So to point out, as the little text says, this task that we do after we do the embedding, so you can think of this essentially as pre-processing of the image. And then what we call the other task that we're doing is a downstream task. So if you ever hear that terminology, that's what it's talking about. You don't need to remember it necessarily, but that's what that terminology means. Cool. Now, there's one final idea about the autoencoder, and I think these two will really like it, which is, what if we change the data? All right, I told you how to get there. Yeah. So let's say now we take a black and white version of the image, we feed it through our autoencoder, and we enforce that it creates a color version of our image. All right? So this is interesting for a couple of reasons. So firstly, ignoring the thing on the slide, we now have a network that is able to recolorize images of this size. That's interesting in its own right. But secondly, we now have some control over what features the network is learning. So in the case of maybe putting boxes over the data, of occluding different parts of it, we could enforce that it finds general features about the entire image rather than specific features. In this case, we're having it learn shapes, not colors. And there's lots of other things we can do to our data. In particular, and one that we're going to look at in the homework, we could add noise to the original image, similar to adding those boxes, but maybe a little bit less explicit, and then try to reconstruct all of the missing details. So this is one way that we're able to actually create those higher res. If you've ever seen this is something we can do, is take an image and increase its resolution beyond what it was originally taken at. And this is how we do it. We have these 4K images, we downscale them to 1K, and then we use the autoencoder to convert them from 1K to 4K. And then we put in other 1K images that don't have a 4K version, and boom, we have 4K. It's very interesting. Those networks use more complicated autoencoders than this, but fundamentally they're doing the same thing, which is interesting. Yeah?
So, if you're creating a black and white image and then you create a colored image,
So in the case of loss, we would first take our original input, and then we would augment it to be black and white. We would feed that through our neural network and get some color output, and we compare it to the original image. So we don't compare it just to this. We now compare it to the pre-augmented, and this will work. Yeah. Interesting, right? Cool. So that's all well and good, right? Anyone have any more questions about autoencoders? These are very interesting. I really like them, and they're very straightforward. Yeah?
How do we actually go about reducing the size of the input? Like,
Yeah.
what method do we use for that?
So in the case of like the neural networks that we've done, right? It's incredibly simple, right? Let's say we have an input size of 784, like MNIST, and we'll have an output size of 784, right? Because they're the same size. And then we'll just have a linear layer that goes from 784 to 10, and then from 10 to 784. Done. So now what happens is that like after the first layer, we have an output size of 10 individual numbers, right? And that is much smaller than the original image. And that's all we need to do. We can also do it with convolutions, but we need to be careful with convolutions. You can imagine if we have these convolutions, like we have a 3x3 convolution, but we have 100 of them, we end up with enough parameters that we can actually still learn an identity function, or at least approximate it. So we do need to be careful of that. But we could also use convolutions to reduce the size. Yeah. Yeah.
So we're just essentially giving it less nodes when we decide to reduce?
Yeah, exactly. Yeah. So these smaller boxes mean fewer nodes in that layer, smaller hidden size.
When you say autoencoder, are you referring to the first part of that model or the entire, like, is that entire thing an autoencoder?
So the entire thing is an autoencoder. So the autoencoder is built of an encoder and a decoder. And then the auto part of the autoencoder is the fact that we have automatically created an encoder out of nothing. We don't have any labeled data. That's where the name comes from. Yeah.
How does this relate to the identity function? Is the green part or is the second half? Is that the identity function?
So we are not learning the identity function. In fact, we're doing this compression. If we had that this center layer was bigger, let's say the center layer was as big as the original input, then it'd be reasonable for our network to just learn 2 identity functions, and there you go. But that's completely and like utterly useless to us, because we could just come up with the identity function. We know what it is. So by compressing the middle bit, we have guaranteed that it cannot learn the identity function, actually. So we can say for certain that none of this is the identity function, actually. Yeah?
Does it guarantee that it won't approximate it?
It does not. In fact, we are actually trying to get it to, in a way. But what we are doing is we're guaranteeing that at least to some degree it is extracting useful features that are not just an identity. If we have this smaller layer size, it can't learn the identity function, so it must combine certain parts of the data in useful ways. And if if part of it is the identity function, that's fine. We still extracted very useful things. We would prefer if all of it is useful features, so playing around with the size of the compression is actually an important thing to do. Yeah.
So essentially with this, you're just learning how to color the image.
In this case.
So, okay, so say, let's do like another example of a transform. So it's a colored image, but let's say we get like an eraser, and we erase your face off.
Okay.
And then we put it through that autoencoder, and then it recreates your face. So now it's learning like eyes and nose and all of that.
Yeah, so that is pretty much exactly what he was getting at with the occluding boxes, which is if we take away part of the image and then we compare it to what it originally was before we did that, it is able to learn these things. This is a point where you guys should probably not overestimate the power of very simple neural networks. It will do very poorly at that. You can try it on your own if you'd like. It's actually very easy to code up these autoencoders, but you'll see that it does sort of fail. It can do all right. It will try putting something there. But it may not look as good as you'd hope. State of the art can absolutely do it, though.
Okay.
Yeah, cool. Any last questions about the autoencoders? We're going to move on to something actually a little bit more interesting and a little bit more difficult. Cool? Cool? All right. That's autoencoders. Now we're going to start talking about generative models. All right, so we looked at that first half, and that's the encoder, right? And now let's think about the other half of that, right? The decoder, right? This is what we had for the decoder. And let's say, it produces some image. Cool, it's a guy now. And we have a little bit of an idea. All right, so we have now that we're going from some low dimensional space, some high dimensional space, right? From small to big. And we think, what if we could put in some noise, just arbitrary noise. Generally, it's Gaussian noise, which is just normal distributions, which are just bell curves. And we sample from those, and we put them through, and we want to produce a face. Right? So this is something that would be very useful for us. We'd like to generate faces. As we were saying earlier, one useful task that we could do with just the data is replicate that data, make new data. So our idea is that we want to somehow learn to generate the real images using just noise. And this should feel somewhat impossible to you. But again, someone very clever came up with a way to do this. All right? I want you to think, though, for a minute. Maybe you can be this really clever person. How might we be able to do this? So this is not the full picture. This is just telling you this is our end goal. We'll be able to take some noise and get some face. How can we do that? Talk in your groups for like 2 or 3 minutes. This is an interesting question, and it is possible. Yeah. Yeah. I think All right. That's enough thinking about a problem that's very hard. So to preempt this, I do want to say that this is obviously a very difficult problem. To tell a little bit of a story of it, though, the guy who actually invented the solution to what we're going to talk about actually invented it drunk at a bar on a napkin, and that napkin has been saved and preserved because he came up with this idea on it. And I also want to say that in hearing different samplings of people's ideas on this stuff, I do want you to know that in general the ideas have been very good. They've actually been pretty impressive. Don't doubt yourself so much if you can help it. And I don't just mean the ones that are said out loud. I've talked to different people, and lots of people have very good ideas. So just believe in yourself a little bit there and have fun trying to think of a solution to this.
Is this a real face?
What do people think? Real face? Fake face?
Also, the last one, is that real?
Yeah. First one was real. This one is fake. Yeah. Fun, right? So, anyone have any ideas that they want to share? There's a pretty good one over here, but if anyone else wants to share first. Yeah? Oh, you're trying to spoil it? No, don't spoil it. All right. Yeah?
I mean, you can train it by, I guess, given, a face, just scramble the pixels around, train it on randomly scrambled pixels, and then, compare it to the actual, unscrambled face, then train it off of that, I guess.
All right, so you're suggesting that we take the original face, we scramble it in some way, and then we compare them?
Yeah, basically.
And we want the network to do the scrambling? So I think you are closing in on autoencoders to some degree. I think I get where you're going with it, but I'm not really 100% sure where you're going with it. I mean, think on it. Usually there is something to ideas. They don't always come across, but usually there is something to them. Would you like to share your idea? Yeah.
Basically, just take what we had before, take the autoencoder, train it through that, and then just chop off the first half.
Yeah, so the idea here was essentially we have the autoencoder, right? So now we take that bit off, we train our autoencoder, and then we take that bit off, and then we feed in noise into that decoder, and we get some outputs. Unfortunately, this idea does not work unmodified. So that would essentially produce noise. If you wanted, you can try it if you'd like. It might produce something that is closer than I'm giving it credit for, but there is actually a modification we can make if we enforce that the center bit is, and this is not the solution to this problem, this is just an aside to elaborate off this. If we enforce that the compression point is what I call it, but that middle bit, the hidden layer of our autoencoder, is exactly distributions, means and standard deviations of normal distributions. We can learn those means and standard deviations and then sample from them to go to the output. That's a variational autoencoder outside the scope of the class, but a neat idea. Anyway, so for this, we come up with a very nice and clever idea, which is, so first I'm actually explaining the problem here. So to get a little bit of an idea of what we're actually trying to do, right, this is a normal distribution, all right? And we want to convert this into some other distribution with a neural network. This is just to get you comfortable with the idea of the fact that we're talking about distributions. If you've taken statistics before, these are distributions. If you haven't, they also are. And in the case of our more complicated example, we're looking at some amount of Gaussian samples, so that is just sampling from bell curves. And we're trying to produce the distribution that is faces. It's a very complicated distribution. So we're trying to translate distributions is really our task. And that's more or less what I describe here. So we're trying to take one distribution that we have known, right? We are generating some data, and we want to get some known distribution, some distribution that we can't model any other way. All right, so we're going to sample from the first one to produce samples from the out one. You can think that we're essentially just making a map from the first set of distributions to this new distribution that we care about. All right? It's just to set up the statistics in the back of your mind. This is how a lot of people think about it. You can choose not to if you'd like to, but it is helpful to think of it this way sometimes. And then we get to the fun idea, which is GANs, Generative Adversarial Networks. Nice. They're a very good one, and they are what we saw earlier with those images that were generating all these beautiful images. They were GANs. So we're going to learn how they work. All right. So first up, we have what we had here, where we're taking some noise, going through some layers, and producing a face, a fake face. And what we're going to do is we're going to call this the generator, right? And then we're going to produce another network that's going to take some image. It's going to go through some layers, and it will determine whether it's real or fake. And we call this the discriminator. These are our two networks that are going to build up our answer to this problem. So, how do we use them? How do we train them to be able to do their jobs? Right? All we really care about, our end goal, is to have a generator that works really well. So how can we train that generator? Using the discriminator. Here's our setup. We're going to have our generator, and it's going to take in random noise. We're going to call Z in this case, so random noise. And then we're going to have our discriminator, and the discriminator is going to take as an input the outputs of our generator. So we're going to generate some image that is the size that we're looking for, feed it into our discriminator, and our discriminator will say fake. Well, it might say real, but we hope that it says fake. And then we're going to take real data, and we're going to feed it into our discriminator. I'm going to call it X here. And we're going to produce the output real, hopefully. So in doing this, we are teaching the generator to produce examples that will fool the discriminator, and we're training the discriminator to be able to tell whether an image is generated or not. And in doing this, they compete with each other, and in the process, both learn against each other. Hence, adversarial. So we have generative, where we're generating these, adversarial, where they're competing with each other, and network, because they're networks. So, as I say here, we want the discriminator to output real if it is real data, and we want it to output fake if it is fake data generated by the generator. All right? We don't necessarily want that, but that's what the discriminator is learning to do. And to make clear, we can represent the real or fake as a single bit. We don't need to represent it as strings or anything. But it's just a single bit, 0 or 1, real or fake. Cool. Now, both of these networks, I'll spoil, are trained gradient descent. We don't need to learn any new training, but there is the interesting question now of what the loss is. So I've said explicitly that the generator is trying to fool the discriminator, and the discriminator is trying to tell whether the generator is real or fake. So, what should the losses be? And in particular, is it a single loss? So I want you to sit on those questions and talk in your group for another 2 minutes. Think about that. All right. What are people thinking? Are they the same or are they different? Yeah. They're inverse. Not quite the right word, but right concept. So what we can notice from this is that, to answer the second question, when the discriminator is doing well, when it's able to tell whether the generator is real or fake every time, by our own definition earlier where I said the generator wants to fool the discriminator, they are completely at odds. If the discriminator does well, the generator does poorly. If the generator does well, the discriminator does poorly. So it's very natural for us to say that the generator's loss is the negative of the discriminator's loss. And that is absolutely what's going to happen. In particular, the actual loss that we're going to use is going to be a bit weird for everyone. But I'm going to show it to you, and I'm going to break it down. I promise it's not as bad as it looks. All right? So here is the actual loss function. Boom. So what this is saying, we're going to break it down, right? So let's break it down term by term first, then we'll look at the whole thing again. Right, so first off, that E of x, right? That is the expected value over all of the real inputs. So that means that first item there, we're looking at all of the real inputs. We're looking at that value for all of the real inputs. So it's feeding through the discriminator to get all the real outputs of the discriminator, I mean. And then we average them. We take the estimated value of that. Likewise, we have E of z, which is the estimated expected value over all of the noise. So every time we take one of the noise, we have to add it to that. And we take the expected value over all of those. Then we have d of x, which is going to be the output of the discriminator on real input. We see that in the first term. And we have a g of z, which is the output of the generator on noise. So if we look at the entire picture here now, we see that this first term, just look at the ex, right, is the expected value of the log of dx. Right? It says, given real input, what the discriminator outputs, and then the log of that. So in this case, we're saying that the real value should output 1. So real is 1. So now if the discriminator outputs 1, and we take the log of that, what is that? It's 0. So if we take the log of a real, so if the discriminator outputs 1 for a real value, then we output 1 here. Cool? And then we take the log of it, then we get 0. And of course, 0 loss is best loss. So that is optimal when it's correct on all of the real data. It's outputting 1 for all the real data. Then we look at the second term. So the second term is saying if we feed in a piece of noise into the generator, and then take that and feed that into the discriminator, then we want the expected value, which we can sort of ignore. You can sort of ignore the expected value for the most part for understanding this. Take the log of 1 minus that. So then in this case, if this outputs 1, that means that it is saying that the generated data is real, if it outputs 1. Then we take log of 1 minus 1 is very big. So in this case, so this is sort of part of the reason that we have these expected values here, is that this will be infinity, which we don't want. So we just say that it's a very high number. We can actually just choose a number to be its maximum bound. And likewise, if it outputs a 0 here, that means that it said that the generated image is fake. In that case, we'd have log of 1 minus 0 is log of 1 is 0. So in the case of the discriminator, this is perfectly good. So this will say if the discriminator is fooled, it has high loss, and if the discriminator thinks that real data is fake, it has high loss. Cool? So now we get to the idea of, we have the discriminator. That's totally cool. But how about the generator? So the generator in this case, like we said, is completely opposed. And we find, in fact, that we can just, instead of minimizing this loss, we can maximize it. So we actually have that the generator's loss is exactly the opposite. It is just the negation of this. So if we go to train this, we can actually just take the loss for the discriminator as its own thing and the loss for the generator as its own thing and train them separately. And that's perfectly all right. We can be a little bit more clever with our coding and take them both at the same time and have one maximize while one minimizes, which we're actually going to do. But for the most part, conceptually, one is trying to minimize this loss value, and the other is trying to maximize it. And you'll notice also that this first term, the log of dx, does not contain the generator at all, so that is actually not part of the generator's loss function. So how does this feel now? Is it less scary now? I'm seeing some wide eyes. All right. Yeah.
Wait, this is just for the discriminator?
So this is for both of them, but this particular loss function is for the discriminator. And then for the generator, it is the negation of this.
Okay.
They're completely opposite. Yeah. Oh, yeah? Okay. Yeah. Yeah. Do we have a homework next week? That's a good question. So yes, it will be due on Friday instead of on Tuesday, though. So give you a bit of time after the exam. It's going to be this one, so it's not one that I want to skip. But hopefully you'll be okay. That homework will not require a ton of coding. It'll be more other stuff. Yeah?
So why do we care about the generator at all for the discriminator's loss?
So because the generator is part of the calculation that comes to it. So the output of the generator is the input to the discriminator. And similarly to how the input matters to the gradient of a linear layer, it matters also to the discriminator. In the case of this also, we care to know whether or not it's a real image or a fake image. It affects the loss. We could have, but this is just the formal way of writing exactly how we would calculate the loss given a generator, given a discriminator. And we do need to actually know the output of the generator to do the loss. Yeah. Yeah?
Even though the discriminator is like downstream from, because wouldn't the derivative like just, if we're doing back propagation, wouldn't the derivative sort of stop at the discriminator before it reached?
So let's imagine, so remember if we have a single linear layer, right, that takes in x and has w and outputs something, if we take the output of that with respect to w, derivative of that with respect to w, it is x. So similarly, the input to our discriminator is going to be the output of the generator. So the output of the generator is actually going to show up in the gradient term. So it is actually related. Yeah, math, right? So for the actual homework, that when you're going to do this math, we will be able to write off with a nice call to neural network dots loss. But I think it is important to understand conceptually what's going on here. Anyway, but don't be too scared by the math. It's not something that we're actually going to need to implement from scratch. But do take a look at it. Cool. All right. So we got 15 minutes left. Cool. So next up, I want you to take a look at these. And I want you to figure out which ones are real. In particular, think about what you look at to tell which ones are real and which ones are fake. All right, all right, all right. Anyone catch any dead giveaways on any of them? Yeah? Earrings, lots of earring talk. Yeah, if you look at the top left, you can actually see that they are two different earrings. Look at that, huh? Yeah, and the bottom right only has one earring. Yeah?
The guy in the middle, his face is too symmetrical.
His face is too symmetrical. Man, I feel bad for the guy. Too beautiful to be real. Anyone else? Yeah. Lighting. Which one in particular? Top middle. That's true, that's true. So that one's fake because the others have good lighting. All right, cool. that's could be real, could be real. Yeah. Yeah? The background.
Backgrounds are mostly blurred in all of the image except the second.
All right, yeah. So all of them are blurry besides the second to the last. Neat, neat. You guys want to hear the answer? Yeah, of course, of course. Yeah, they're all fake. But it gives you a chance to see that, one, it's hard to tell if it's real or not. And what you guys were just doing is acting as the discriminator, right? So that is the job that the discriminator learns how to do. Right, and you can see that it's pretty hard, and these are these are actually generated by a GAN. So that means that there's a discriminator that accompanies it that can tell these apart roughly. Very neat, very neat. Cool. I also want to show you something that I find pretty interesting, which is because we're sampling from distributions that we know, we can actually change those distributions a little bit and continue to sample nearby points. And because of that, we can actually get visualizations of what very nearby samples look like after going through the generator. And they look something like this. Oh, isn't that weird? There are very good other ones of these. This is the best one I could find on short notice. But yeah, you can see that it's very similar in the generator's output when we have a similar input from the noise. These are called walks. Yeah.
What's the deal with the facial expressions?
So the facial expressions are somehow represented in the noise, and we're doing a walk over those as well. So we can actually find that when we take this, we might be sampling from like 5 or 6 different distributions to get it, and we can just change one of those distributions, and it will change one of the features of the outputs, which is really weird. It makes us feel uncomfortable. Yeah, right? Okay, cool. Enough of that. So this brings us now to GANs are amazing, right? We love them. We love them. Everyone loves GANs. But there's a bit of a problem with them in terms of practicality. In particular, they're extremely finicky. So we've talked a little bit about hyperparameters and finding the best hyperparameters. You guys had to do a little bit of that. But now all of a sudden, it's actually very hard for us to find good hyperparameters. We're doing this very complicated task where we are transforming some small distribution into this very complex, interesting distribution. And that requires a lot of searching to find a good answer. Also, the initialization of the network matters a lot as well. So all these things come in to say that training a GAN is actually very hard practically. So I think it's about time that we talk about how to find good hyperparameters, how to do hyperparameter searches. Yeah?
Why can't we just do like stochastic gradient descent on the hyperparameters again?
So he's asking how come we can't do stochastic gradient descent on the hyperparameters. I'll give you 2 answers. One, what would the computation graph of the loss over many runs of our network, many trainings of our network to a hyperparameter look like? The short answer is it's tremendously hard to calculate that. So if we want to calculate it, we have to differentiate through the entire training process to get back to that. The second answer, which is a bit of a cheeky one after I said that, is people do it. So you can. It is not particularly practical, but if you're interested in looking into it, you should look into meta-learning, which is learning to learn. And in doing that, they learn their hyperparameters this way. There are also ways that we can approximate the running of the network, the training of the network, and these sorts of things. But really, it is just an improbable thing to actually try to calculate exactly. But you can estimate it. So people do try it, but there are better ways for us to do it. So first up, I just want to point out overfitting. So we've talked about overfitting a little bit, right? But let's look at an example. Say we have 8 from MNIST. And let's say that every 8 in our data set has a little red square in the corner. Right? So we train on this data set, and every 8 has this little red corner. And it learns that these are 8s. Cool. So what might happen if we take this image of an 8 after we've trained on this data set of red square 8s, and we take away the red square? What might it do? Yeah?
It might still stay as an 8 because there's a red square.
Oh, if we take away the 8? Oh yeah, with 8 without it. So I was suggesting we take away the red square, which means that kind of the opposite. It might not say it's an 8. But similarly, if we train on this too much, it may say that the red square is the 8. That's the thing that matters. So we may find that if we give it an image of just a red square, it would say that's an 8. And this is an indicator of the idea of overfitting. So I want you to talk in your groups for like a minute or two about this issue. Is this a real issue, or is it only an issue when I add red squares to 8s? Give it some thought. All right, gonna call it there. So hope you all thought about it. And in fact, this is a big issue in all data. But not only is it a big issue in all data, it is sort of what we do in all data. Similarly to how when I was talking about the like race fitting, how we saw that we fit with race really well. Similarly, we identify these biases in the data. We see that a red square means an 8 because that's what we're told in our data. And learning it is not necessarily the fault of the model, so much as it is the fault of us for messing up the data set and allowing it to overfit. So overfitting being that we don't test it on anything other than how well it does on these data that have this red square. And we can think of this red square as being a number of different attributes of our data. Maybe our data set only has white people in it. Then very similarly, it's only able to identify faces of white people. This is a very real example. Go try out the CV2. You'll see that it's real. It really can't identify non-white faces. And this is an issue that we have in a million different ways. And it happens in ways that we really can't see either, deep in the data. So how do we deal with that? So the first concept is something we've already looked at, which is we're going to have a training set, which is what we're going to actually train our model on, and then we're going to have a testing set, which is going to be a separate data set. So we've done this in our homeworks. You may have caught on to it. The reason being, if we only look at our performance on our training set, and we don't ever look at any other data set, then if it fits really, really well to that training set, we say, great, ship it out. And we never actually have it tried on different data to see if maybe it's just learning the data really well. You can imagine a very severe situation would be maybe it can exactly learn the training data. It just memorizes all of the training data. And then if it sees any other data, it completely fails. If we have very small training data, that can happen. So this is an issue, and this is a rudimentary solution. All right, let's try it on a different data set. If it performs well on that, cool. But that doesn't really answer a big question that we care about. And one thing to note about this is if it does very well on the training set and does poorly on the test data set, then it's very likely overfitting. This means that because they're from the same distribution, the test and the trained data set are from the same distribution, if it only does well in the trained data set, then to some degree, it is memorizing patterns in that data set in particular, not the overall distribution between the train and the test. And that's an issue. We don't want to see that happen. But it doesn't answer a big question for us, which is, we have these hyperparameters that we've been using, learning rate, hidden layer size, convolutions have a whole bunch more. How do we know the best ones, right? And as he pointed out, we could try doing gradient descent to them, but that's difficult. And there are simpler ways that we can try little things that allow us to find better ones than we had before. So first up, just to point out, we do not have a way to find optimal ones, perhaps besides doing gradient descent on them and trying that, although it is totally infeasible. We also don't want to just guess and check. So on these homeworks, I would expect that most of you guys just try different values. Turn up the learning rate a little bit. Does it work? Turn it down a little bit. Does it work? And try that over and over again until we find something good. We also don't want to do that. That's a big waste of our time. And you'll be sitting there thinking about these a little too hard, because it's very hard to tell how the learning rate affects the outcome. It's not really a simple function. It's pretty complicated, as we saw with this whole meta-learning thing. It's a very difficult thing to actually comprehend. We can guess it, but we're also pretty bad at it. So I'm going to skip this because we're a little bit low on time. But if you think about it a little bit, there are some naive ideas we might want to try. And the most obvious is do a search, like a for loop. Let's look at how that goes. Right? So let's look at a grid search. So grid search is going to be the one that if you are lazy, you're going to do, which is we do a for loop over one of our hyperparameters. We do a for loop over the other. And then we train our model given those parameters and see how it performs on the test data set. And then if it does well in the test data set, we say good, it generalized. And does poorly, we say it didn't. And we try all of these and we see which one's the best and we say that's the one. Very simple, very elegant, I suppose, but it's also very naive. And there's a couple issues with it. Let's look at one issue real quick. So let's say that this is the possible spaces of all of our hyperparameters. I drew it as a box. And let's say that these are just the hidden layer and the learning rate, right? And I'm going to do a bit of a weird visualization here just to make a point, which is let's put the performance. Let's say that we can get the performance with respect to just that parameter, and let's draw it. So these red curves are the overall performance. So the higher, the better, right? If we plot all of the search we do in a grid search, right, we're just going through here, and we look at how it lines up, we can see that for the most part, we actually hit these minima, right? We got unlucky. We're only checking a few different settings of this hyperparameter, and because of it, we're missing, you see on the right, there's a very good optimal right there, right? So we're missing that. So what if instead we did it randomly? We just randomly set them, and then you see here, because they're all different, we actually check more of each of the different types. So we check over the range more finely. We tried more different values. And because of this, we're much more likely to find one that's very good. We're a little bit less consistent in them, and we can say a little bit less about how one hyperparameter affects the outcome of the model, but we could get better outcomes. And that's called random search. These two are your friends. They're very easy to implement, and they're very nice. Cool. These are not the end-all, be-all for finding hyperparameters, but it is all I will ask of you in terms of actually writing a search. And last up, I want to say that we can also use our training set to test. Here's what I'm talking about. So we take our training data set and our testing data set, and instead of just training on the training data set and testing on the test data set, we're going to separate some amount of the training set as a validation set. So now what we're going to do is we are going to train on the training data set. Actually, I'll say here. So we're going to train on the training data set, test on the validation set, and then save the testing data set for us to be able to check against later. This allows us to not overfit on the testing data. It's a whole extra layer of that. Because you can think if we manually change the hyperparameters, if we do gradient descent on the hyperparameters, for example, we'd end up with hyperparameters that are overfitting on the testing data set now. It's still happening. So we actually introduced this validation set, which is essentially just a testing set that we have separated out from the training set. And we're low on time, but I'll try to get through all of this.